Okay, the masked professor is on the air again. Today we will be studying the fascinating subject of the t-distribution. Now, the t-distribution is a normal distribution, but with the variance unknown. Pardon me for removing my mask. It's very difficult to spend a lot of time speaking with one of these on. All right, so let's talk about this, and we'll learn how to do the confidence intervals with it. All right, so let x1, x2, up to xn be a random sample from a normal distribution with unknown mean mu with a known mean mu and an unknown variance sigma squared. I can't believe they let that sneak by them. The random variable t equals x bar minus mu divided by the quantity sample standard deviation divided by square root of n has a t-distribution with n minus 1 degrees of freedom. Okay, so degrees of freedom are going to be part of what we are going to be looking at in the t-distribution. And again, degrees of freedom in this case, all it means is n minus 1. Okay? Later on, when you do inferential statistics, you'll get to do the F distribution, where they have a numerator degrees of freedom and denominator degrees of freedom. And I know many of you right now are saying, F that. Okay, I'm sorry. I love making that joke. All right, so if x bar and s are the mean and sample standard deviation of a random sample from a normal distribution with unknown variance sigma squared, a 100 times the quantity 1 minus alpha percent confidence interval on mu is given by x bar minus t alpha divided by 2 with n minus 1 degrees of freedom times sample standard deviation divided by the square root of n is less than or equal to mu less than or equal to x bar plus t alpha divided by 2 with n minus 1 degrees of freedom times sample standard deviation divided by the square root of n. That is where t alpha divided by 2 with n minus 1 degrees of freedom is the upper 100 times alpha divided by 2 percentage point of the t-distribution, again with n minus 1 degrees of freedom. One-sided confidence bounds on the mean can be found by replacing t alpha divided by 2 with n minus 1 degrees of freedom in this equation with t alpha and n minus 1 degrees of freedom. Okay, so it's not huge and mysterious. This is very much like exactly what we have been doing with the standard normal distribution. All right. And here we have a problem in the t distribution, however, let us look here at our t distribution table. All right, our t distribution, you'll notice it's still a normal curve, but it's set up somewhat differently. You notice these numbers here, they are not the probabilities. Instead, our alpha probability is across the top. So we go from 0.40 to 0.25 to 0.10 to 0.05 to 0.025 to 0.01 to 0.005 to 0.0025 to 0.001, and then finally to 0.0005. All right, so that is where we look for our alpha or our alpha divided by 2, depending on whether we're doing a one-sided confidence bound or a two-sided confidence bound. Now, you'll notice the symbol here. Well, maybe you won't notice it. It's pretty tiny. All right. You'll notice our symbol here is kind of a funny looking V. That is the Greek letter nu. Okay? Nu, N-U, and not M-U, mu. I know, it's kind of confusing. All right, and these are the degrees of freedom, right? So that funny looking V is equal to n minus 1. All right, so if I am looking at an alpha of 0.10 and I have 11 samples, I am going to look here at 10 and come across to the column that has 0.10 here, and I would say my T alpha with n minus 1 degrees of freedom is 1.372. All right, so now I'm not just going to stop there. Instead, I'm going to go through some examples of how we find our T alpha divided by 2 and how we find our T alpha with whatever number of degrees of freedom. All right, so I brought my good old 5th edition book. All right, so problem 8-23. Yes, well, let's widen that out a bit so that we can see it. All right. So, part A it says if our confidence level is 95% and our degrees of freedom is equal to 12. All right? And this is for a two-sided confidence interval. All right. Skipping a bunch of calculation, we know that for a confidence level of 95%, that means that alpha is going to be equal to 0.05. That implies that alpha divided by 2 is equal to 0.025. Okay, so far, so well. Now, so we know that alpha divided by 2 equals 0.025, that our degrees of freedom is equal to 12. So I get my famous T-table out. This is the first time I've found having that loose leaf book be a really useful thing. All right, so I've got my T-table. Just like I did with the standard normal distribution, first of all, I'm going to say, what is my alpha divided by 2? Oh, here. Okay, I went a little too wild. We can't see new. Or maybe we can if I move this over. All right, I'm going to have to break down and make it a little wider. All right, there you go. All right, so my alpha divided by 2 is 0.025. Then I'm going to follow over here my degrees of freedom, my number 12. So that now I say my T alpha divided by 2 with n minus 1 degrees of freedom. So my T of 0.025 with 12 degrees of freedom is 2.179. See, easy enough. All right, now let's do part B. Part B again, wants a confidence level equal to 95% and a degrees of freedom equal to 24. All right, so 95% means that alpha equals 0.05, implying that alpha divided by 2 equals 0.025. Okay, easy enough. So now we have our all right, I hope you guys can see that well enough to see what's going on. All right, so once again, I choose my, wrong column. See, that's one thing about all these tables, you can screw up. All right, so here's my 0.025 column. All right, and you'll notice we're only going up to 19 here, so I will tilt down and put a piece of paper under my row of the degrees of freedom being equal to 24. Right? So I come over here and I have my T of 0.025 with 24 degrees of freedom as 2.064. All right, so I move my table out of the way. T of 0.025 with 24 degrees of freedom equals 2.064. Okay. So let's move on to part C of this problem. All right, now our confidence level is going to be equal to what? Oh, tricky, 99%. And our degrees of freedom is equal to lucky 13. All right, at a confidence level of 99%, that means that alpha is going to be equal to 0.01, implying that alpha divided by 2 is going to be equal to 0.005. Okay, so we have our alpha divided by 2 because this is a setup for a two-sided confidence interval. Yeah, there you go. That's not too bad. All right, so I look for my 0.005, okay, and that is the column just to the left of my piece of paper there. Then I look for my degrees of freedom, which is lucky 13, and where my pieces of paper form a corner, that is my T of 0.005 with 13 degrees of freedom. 3.012. All right. So T of 0.005 with 13 degrees of freedom equals 3.012. Oh man, they've given us a really challenging one for part D. Here, the confidence level is equal to 99.9%. And the degrees of freedom is equal to 15. All right, so what is my alpha at a confidence level of 99.9%? That means that alpha is going to be equal to 0.001, and that implies that alpha divided by 2 equals 0.0005. We want T of 0.0005 with 15 degrees of freedom. Okay, well, luckily, our table goes that far. Unfortunately, I'm not going to be able to show, if I leave it at this size, I'm not going to be able to show everything I might want to. 4.03. So I'm going to have to widen out a little bit. All right, there you go. And go like this. And there we go. Now, I put my piece of paper as usual on here, although in this case it is the furthest column to the right. So I guess I could have skipped putting that first piece of paper. Right? So my column of 0.0005, then I'm looking for my degrees of freedom at 15, and I follow it over until these two papers form a corner, and I say that is 4.073. Okay, well, how delightful that is. 4.073. Now, you'll notice I did not work it out from the confidence interval percentage equals 100 times the quantity 1 minus alpha percent formula. Okay? I did that at first so that you would understand better. But now you need to start transferring your knowledge to being able to look at it, and only in the most obscure cases going through all that calculation. So obscure. Okay, well, of course, when we do a two-sided interval, that implies that there are one-sided intervals in the universe. So, problem 8-24 is about T alpha with n minus 1 degrees of freedom. All right, so part A, and what do we have? All right, so our confidence level percentage equals 95%. Our degrees of freedom equals 14 in this case. All right, so the confidence level at 95% implies that alpha equals 0.05. Therefore, we are going to be looking for T of 0.05 with 14 degrees of freedom. Right? Again, this is one-sided confidence intervals. All right, so once again, I pick up my cudgel, and I put a piece of paper down so that my .05 alpha column is shown here. Then I'm going to put a piece of paper across at my 14, right where we make a corner, 1.761. All right. Let me make sure. Ah, good. We can still see that. All right, I may have to start throwing away some of these pieces of paper. You'll notice they're getting a million dots from the Sharpie bleeding through. All right, so part B, our confidence level percentage equals 99%. Our n minus 1 n minus 1 is 19. All right, well, this implies that alpha equals 0.01. Therefore, our T of 0.01 with 19 degrees of freedom I know, I can hardly wait to find out. Oh, perfect. All right, so I look for my 0.01 column, right? So that's right here. And then I look for my 19 row. All right, and you'll notice that right here in the corner, 2.539. So therefore, T of 0.01 and 19 degrees of freedom is 2.539. All right, and part C, the confidence level percentage is equal to 99.9% with a degrees of freedom equal to 24. Now, on your table, they have every digit from 1 to 30, and after that, it starts skipping, and you have a degrees of freedom of 40, 60, 120, and infinity. That's what I'm looking for, that infinite curve. All right, so that means, that implies alpha is 0.001. Therefore, we're looking for T alpha, or excuse me, T of 0.001 with 24 degrees of freedom. Right, well, how exciting that is. All right, oh, well, all right, so let's start up here, because I am going to have to bend down a bit. All right, you can see over there on the right-hand side, the second column from the right is the 0.001, excuse me. All right, so I put my piece of paper down there. Then I take my other piece of paper and I put it down on the 24 row. And you're saying to yourself, wait a minute, I can't see 24. All right, here. All right, so I put it down on the 24 row, and right here in my little corner, 3.467. 3.467 then is our T of 0.001 with 24 degrees of freedom. All right, so you can see our procedure to find this is a little more complex than we would like, but is only a bit complicated. It's not rocket science. Hey, come back here. Did you see that? That candy tried to escape. All right. Now, of course, everything that I do here today, I am going to go ahead and make a PDF copy and put it in Moodle for you to have and to hold. I'm tempted to say, till death do you part, but that sounds too dramatic. All right. So, let's work on problem 827. Okay, so let me write down given. A research engineer for a tire manufacturer is investigating tire life for a new rubber compound and has built 16 tires. Okay, 16 tires, that's our N. And tested them to end of life in a road test. The sample mean and standard deviation are 60,139.7 kilometers, and our sample standard deviation is equal to 3645.94 kilometers. right? Everything's on there, good. Okay. And they want a 95% confidence interval. All right, so we remember our confidence interval formula. X bar minus T of alpha divided by 2 with n minus 1 degrees of freedom times our sample standard deviation divided by square root of n is less than or equal to the mean less than or equal to our sample mean plus T alpha divided by 2 with n minus 1 degrees of freedom times our sample standard deviation divided by square root of n. Oh, thank dog it all fit. All right, so what is our T alpha divided by 2 with n minus 1 degrees of freedom? All right, well, a 95% confidence interval implies alpha equals 0.05, and therefore that implies that T of alpha divided by 2 is 0.025 with n minus 1 degrees of freedom, right? N is 16, so n minus 1 is 15. And what is that equal to? Using a well-worn theme, I'm going to come here and I'm going to put down my sheet of paper by the 0.025 column, and under my n minus 1 equals 15 row. All right. I go for my corner and it's 2.131. .131. All right, well, now we have everything we need. So 60,139.7 is our sample mean, minus 2.131 times our sample standard deviation, 3,645.94 kilometers, and that is divided by square root of 16 is less than mu is less than or equal to 60,139.7, our sample mean, plus 2.131 times 3,645.94 divided by square root of 16. All right. All right, so let's save this, save as, basic statistics and probability, chapter 8, T distribution. Problems. Oh, well, that was stunning in the way I did that. All right, and of course, what have we got? We've got equals 139.7 minus 2.131 times 3645.94 divided by square root of 16 for my lower bound. And there's my upper bound. So the lower bound is 58,197.3. $58,197.3 less than or equal to mu less than or equal to 62,082.1. Yes, okay. 62,082.1. And both of these are in kilometers. All right. So that's our two-sided confidence interval. But what if we want to just make sure that our tire lasts for a certain number of kilometers? In that case, we would do a one-sided lower bound calculation. Okay, well, that 95% confidence interval implies that alpha is going to be equal to 0.05. That means we want T of 0.05 with n minus 1 or 15 degrees of freedom. All right, so once again, I pick up my table, and oh dear, what did I do with my pieces of paper? There they are. All right, so we want at 0.05 I put my paper down right by that column. Then I want 15 degrees of freedom. All right, so here we have it, 15 degrees of freedom, 0.05, 1.753. $1.753. We know the formula for our lower confidence bound is x bar minus T alpha with n minus 1 degrees of freedom times sample standard deviation divided by square root of n less than or equal to mu. All right, we substitute in 60,139.7 kilometers minus 1.7353 times there you go, 3,645.94 divided by square root of 16. Okay. Oh, and of course that is less than or equal to mu. All right, so we've got that. And I do my calculation here. 1.753. I'm cheating by just going off what I did before. All right, so my calculation when I do it is 58,541 point, call it 9, less than or equal to mu. All right, so using a one-sided confidence interval, we say that we are 95% confident that a tire will last at least, on average, 58,541.9 kilometers. Now, if we're worried about having our average be above 55,000 kilometers, man, we're golden. We're there. All right. All right, I'm going to start eliminating the speckled paper. It's not like I have a shortage of scratch paper. All right, well, all right, so let's do problem 829. A post-mix beverage machine is adjusted to release a certain amount of syrup into a chamber where it is mixed with carbonated water. A random sample of 25 beverages, so N equals 25, was found to have a mean syrup content of X bar equals 1.1 fluid ounces. So X bar equals 1.10 fluid ounces of syrup. And the standard deviation is sample standard deviation equals 0.25. .25 fluid ounces. All right, and they want a confidence interval equals to 95%. Now, in the book, it just says a confidence interval of 95%. I'm going to interpret that as they want a 95% confidence interval on the upper bound, because when we're selling sodas, we don't want to give away too much syrup on any particular soda. All right, so 95% implies alpha equals 0.05. That means our T alpha with n minus 1 degrees of freedom is T of 0.05, and our sample size is 25, so n minus 1 is 24. And what is that number? Didn't we do this problem earlier? Maybe we did. It won't hurt us to do it again. All right, so I've got my table here. I take my pieces of paper and I put one by the 0.05 column. All right, now I have to go down a little bit so that I can get to my n minus 1 equals 24. Okay, and as you can see here in the corner, the T of 0.05 with 24 degrees of freedom is 1.711. Oops, too far down. All right, there we go. our upper bound formula is that mu is less than or equal to x bar plus T alpha with n minus 1 degrees of freedom times sample standard deviation divided by square root of n. So mu is less than or equal to 1.10 fluid ounces plus our T alpha with n minus 1 degrees of freedom, which is 1.711, times our sample standard deviation, or 0.25 fluid ounces, divided by the square root of 25. Oh man, I barely made it. Okay, so we know we can say already mu is less than or equal to some amount of fluid ounces. So let's calculate that. Equals 1.10 plus 1.711 times 0.25 divided by the square root of 25. All right, so our number becomes mu is less than or equal to 1.19. Well, there you go. Wasn't that exciting? All right, let me check the time here. All right, so we did problems on how to find our T alpha divided by 2 with n minus 1 degrees of freedom, on how to find our T alpha with n minus 1 degrees of freedom, with how to do a two-sided confidence interval, how to do a lower bound confidence interval, and how to do an upper bound confidence interval. Okay, well, I'm feeling all excited and happy. All right, so what I would like to do now, switch over to computer. And make this large enough to see. Now, you may be asking yourself, why the hell does this bald guy keep showing us how to do problems in Excel? Look, any of you that end up doing statistics, and I'm looking at you, particularly environmental science students, are going to have to be able to put data into Excel and make it sit up and beg. Okay, so a word to the wise is sufficient. For you guys in engineering, this is also an important skill. All right, so let's see, I'm at 200%. That should be good. And let's look at problem . Here we go. This is a good one. 8-34. In 8-34, we are given the solar energy consumed in trillions of BTUs in the U.S. by year from 1989 to 2004. Source, U.S. Department of Energy website, blah, 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 is shown in the table below. Read down, then write for year. Oh, bloody hell. All right. All right, so from 1989, that means the next year is 1990, for those of you who weren't sure. No, I'm kidding, of course. All right, and pull that down until I have 2004. Uh-oh. All right, there. All right, so we've got year, and we have our XIs. So, in trillions of BTUs, starting here, 55.291, 59.718, 62.688, 63.886, 66.458, 69.857, 70.833, 70.237. Oh, you're kidding, it went down? Huh. That's a surprise. Oh, okay, I get it. 69.787, 68.793, 66.388, 65.454, 64.391, 63.62, 62, not 63, and 63.287. Uh-oh. All right, I missed one somewhere here. Let's look here. All right, sure enough. All right, so 55, 59, 62, 63, 66, 6, up, there you go. All right, so a couple of things. First of all, you observe that an old hand like me at inputting data realized immediately that I had made a mistake because it only came up to 2003, and I had been careful to put down 2004. Another thing you notice is the values are going up as far as how much energy is being expended until in 1997 it starts coming down. Why did that happen? Well, because there has been a huge push for more and more energy efficient cars, appliances, houses, which has caused our engineers to re-look at products and say, how can we make this better? If you have a house that was built a long time ago, like my little house in Corpus, which was built in 1947, there's no insulation in the walls. It was built at a time that energy was so cheap that they weren't worried at all about insulating the walls because insulation was very expensive compared to the savings in energy. Of course, now we go back into a lot of those old houses and we retrofit them to have insulation, because now it's very expensive not to have insulation. But I digress. All right, so we want to have our X bar. We want to have our sample standard deviation. We want to have our, should be lowercase n. And we want to have our sample size. Well, from the problem, we can already say sample size is 16. X bar, of course, equals AVERAGE, left parenthesis, not of the years, but of the energy construction, the energy usage in trillions of BTUs. All right, so we've got that. We want to have our standard deviation for a sample, and again, all we do is highlight our numbers. All right, so we've got our numbers. What we don't have, let me think, let me look, all right, so they want a 95% confidence interval. So that implies that alpha is 0.05, that alpha divided by 2 equals 0.025. And that T of alpha divided by 2 with n minus 1 degrees of freedom is how much? All right, well, one thing I could do, let me see if I can remember how to do this correctly. Equals T distribution, two-tailed, so 0.05, comma, degrees of freedom is 15. Is that right? Oh, hell no, I don't believe that's right. So I check myself before I wreck myself. As the old saying goes. And I look at 0.025, which is my alpha divided by 2, and my 15 degrees of freedom, which says that it should be 2.131. Oh, I'm so disappointed. All right, so what did I do wrong? Let's try inverse T. All right, let's not try that then. T distribution. Boy, I did this a second ago and it just popped right up. Ah, there we go. How about T inverse? All right, and what do we want? Oh, we want the probability 0.05 and the degrees of freedom at 15. And get rid of that. There you go. See, it gave us our 2.131. All right, now we have all the numbers we need to perform brain surgery. Construct a confidence interval. All right, so just to remind you, because there, as the old song reminds us, there is always something there to remind you. All right, so x bar minus, x bar minus T of seems like it's never the one you want. Alpha divided by 2 with n minus 1 degrees of freedom times S divided by square root of n Okay, you'll notice the formula thing automatically put the divided by square root. That's perfectly valid mathematically, so I am just not going to worry too much. All right, well, I know I'm gonna, oh, that's not what I wanted. All right, now you're making me mad here. I'm gonna want mu, but then I'm gonna want math symbols, and right in front of mu, I'm gonna want less than or equal, and right after mu, I'm also gonna want less than or equal. All right, and once again, I subtly steal and place on my right side and just replace the minus with a plus. Okay, boy, that is small. Okay, what's the deal? Do both sides the same here, guys. All right. All right, so now we've got our formula here for a 95% confidence interval. Well, for any two-sided confidence interval where we are using the t distribution. All right, so we know this is going to be less than or equal, less than or equal to mu less than or equal. All right, so what is our lower confidence bound going to be? It's going to be equal to our x bar minus our t alpha divided by 2 with n minus 1 degrees of freedom, in this case 0.025 and 15, times our sample standard deviation divided by the square root of 16. All right, so that's 63.3257. All right, now on this side, we're just going to do the same thing with a slight variation. Our x bar plus our t of 0.025 with 15 degrees of freedom times our sample standard deviation divided by square root SQRT of n. All right, so we can say that this is missed the T there. All right, there you go. All right, so 6.325 or 326 trillions of BTUs is less than mu is less than 67.829 trillions of BTUs. And we'll, here we go. Let's do it like this. And I'll just move this over a little bit. All right. So you can see This wasn't too difficult. We've got to sort through the data, establish what our formula is, in this case for a two-sided confidence interval, plug the numbers, and Bob's your uncle, we're there. All right, so this is problem 8-34. Now, I hope you guys are actually looking at these materials and I'm not wasting my time creating them. Because believe me, 2 more lectures, I could be done with chapter 8. But I want to take it slowly, section by section, so that you'll have some better understanding. Let's see, one more problem, and I promise I'll stop. All right, so problem 8-33. It's going to be another year and XI problem. All right. And let's run this. Hey, what happened? Oh, okay. Let's run up the size on this so that you guys can see it. Maybe I should go ahead and delete that. Yeah, there you go. All right. The Bureau of Meteorology of the Australian government provided the mean annual rainfall in millimeters in Australia from 1983 to 2002 as follows. All right, so 1983, 1984, I don't know if they made y'all read 1984 in school. That was certainly part of, only to 2002, pardon me. That was certainly part of my education. Very exciting. All right, so the numbers, they don't tell us how to read them, so I'm going to read them in my own individual way. 4.99.2, 555.2, oh, what a mistake on my part. All right, 398.8. Oh, bloody hell. All right, here we go. 555.2, 398.8, 391.9, 453.4, 459.8, 483.7, 417.6, 469.2, 549.9, 452.4, 499.3, 340.6, 522.8, 469.9, 527.2, 565.5, 584.1, 727.3, 558.6, and 338.6. Oh, phew. It came out even this time. Don't have to worry about having missed a number. All right, because it's rainfall, I assume that we want a two-sided confidence bound again. So let's see. Construct a 95% confidence interval for the mean annual rainfall. All right, so my X bar equals my sample standard deviation, my number of data points, my T alpha divided by 2 with n minus 1 degrees of freedom, and of course, what is my, alpha? All right, at 95%, that means that my alpha is going to be 0.05. My function is T dot INV for inverse, 2T for two-tailed, the probability and what is my degrees of freedom? All right, so that's 20 years of data, and that means that it is 20 minus 1 degrees of freedom. All right, 2.09302. Now the great thing about using Excel on something like this is your Z tables, that is the standard normal distribution tables, are pretty detailed. This bad boy, the T table, however, not so much. All right, so we know, and I could do it the fancy way, equals count, left parenthesis, right parenthesis, equals average, highlight my numbers again, right parenthesis, got that, equals stdev dot s, left parenthesis. Once again, I just illuminate or highlight all my numbers. right parenthesis. All right, so now I've got my numbers. Let me see if I can copy from. Okay, I can copy, but it's super giant size. Ah, bloody hell. Let's see if we can. All right, there you go. Uh-oh. I lost it. Why do they make it such a pain to do this? All right, well, class is getting really late, so let's just move quickly. All right, less than equal mu less than equal. All right, so my left side of the equation equals my x bar minus my t of 0.025 with 19 degrees of freedom times my sample standard deviation divided by the square root of my n. All right, so 443.475, or call it 0.5, is the lower end, equals x bar plus my t of 0.025 with 19 degrees of freedom times my sample standard deviation divided by the square root of my sample size. And there you go. There is our famous confidence interval at 95%. All right, well, we have actually gone pretty long compared to what I expected to do today. So, please stay safe, and when the fields are white with daisies, we'll meet again.